yes, welcome everyone to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Eora Nation, and I'd like to pay my respect to the elders past, present and future. So I'm thrilled to have Asbjørn Christensen joining us today. So Asbjørn is the owner of Nordic Geoscience, consulting worldwide on ground and airborne geophysics for resource exploration. He's worked on minerals and petroleum exploration projects in Australia, Asia, Africa, Europe, and the Americas, with his areas of expertise in airborne geophysics, potential fields, 3D geological and geophysical modeling, and the integrated interpretation of geophysical data for minerals and petroleum exploration. So with his vast expertise, it is going to be wonderful hearing from him today about exploring with airborne gravity radiometry. And it's going to be an awesome session. I hope you all enjoy it. Please use the chat and we'll be opening up the floor at the end. And yes, thank you so much, Asbjørn, for joining. It's amazing having you.
Thank you very much, Jessica. Thanks for giving me the opportunity to talk to you this afternoon in Australia. And the presentation that I'm giving today is a much shortened version of a course that I've been running in airborne gravity gradiometry over the years. So I really should acknowledge some of the slides that was made by Mark Dransfield and other former colleagues from both Fugger Airborne Surveys and CGG. Now, without further ado, what we're going to talk about today is how we can use airborne gravity gradiometry in our exploration efforts. And so what we're going to cover today is basically, first of all, there we go. First of all, how AGG differs from conventional gravity. We're also going to see how the noise levels and the spatial resolutions of airborne gravity gradiometry affects what you can detect in surveys. I'm going to teach you how to design an airborne gravity gradiometry survey, and then we're going to look at some case studies that are going to include both regional mapping, iron ore exploration, and iron oxide copper gold exploration. Now let's see if we can get the next one going. Now, the gold standard in gravity acquisition is ground gravity, and whilst it produces good results, the word that comes to mind if you want to describe it is slow. Its regional coverage is very time consuming. These two lads over here in this picture here would probably take about a day to do between 80 to 100 stations. Of course, you also need ground access. However, if you have that ground access and go through the effort of doing ground gravity acquisition, you can get up with data that has good accuracy and good resolution. For example, as an example, there's the area here. Which is a ground gravity survey over a meteor impact crater in South Africa called the Redford Dome. And within the center of the structure, data has been acquired with 500 meter station sampling. But further away, you have increasing station spacing. So you have stations up to 2 to 5 kilometers apart. If we compare this with airborne gravity, then the advantage there, of course, is that now we put the graviometer in an airplane, and so we have faster speeds of acquisition. You're flying over the ground instead of walking on it, so there are much fewer access issues. And because you're having more rapid acquisition, your costs are typically reduced. Unfortunately, airborne gravity gives you reasonable accuracy, but poor resolution. So typically, from an airborne survey, you get an accuracy of about 1 milligauss, and you would have a wavelength of about 3 kilometers. So unfortunately, that is inadequate for most mineral exploration projects. For comparison, we now see the same area over the Eötvös Dome in South Africa, but now resulting from an airborne gravity survey having been flown at 4-kilometer line spacing. And you can see that we have now complete coverage over the area and uniform coverage over the area, but we're suffering from reduced spatial resolution. However, airborne gravity gradiometry combines the best of both worlds. It's airborne, so you have fast acquisition speed, few access issues, and the cost is reduced because of that. But you also get both good accuracy and good resolution. And with the sort of top of the line instruments today, you can get an accuracy of about 0.1 milligal with a half wavelength, or with a wavelength filtered at about 300 meters. So you can get 150 meter resolution. And so for comparison, here is an airborne gravity gradiometry survey that's flown over Eötvös Dome with 400 meter line spacing. And so we see that when we compare the surveys, here we have the ground gravity survey, here we have the airborne gravity survey. The ground gravity survey was slow, and it doesn't have complete coverage. The airborne gravity survey was fast, has complete coverage, but poor resolution, whereas the gravity gradiometry survey has the best of both worlds. It has complete coverage and good spatial resolution. So if we just consider how is it that we do ground gravity acquisition, and I'm going to walk you through this just to try to explain the difficulties that we have with the airborne acquisition of with gravimeters. If we are on the ground, a gravimeter is really nothing more than a test mass that's hanging from a spring, and that spring will extend or contract depending on whether you are over a mass excess or a mass deficiency. And so by mapping the expansion or contraction of the string, you can get an image of the gravitational attraction over your profile. And from that the variation in gravitational pull, we can then say something about what is the density distribution in the Earth below us, which is exactly what we're looking for as explorers. However, ground gravity comes with an awful lot of compensations. The signal itself, the observed gravity, is something in the vicinity of 980,000 milligauss. And after that, there's a slew of corrections that you do. There's the reference ellipsoid, there's a free air correction, there's the boogie slab correction, there's a terrain correction, there's a tidal correction, there's an isostatic compensation correction as well. Before, once having done all those corrections, we're left with the residual, which is the gravity effect of the geology. And the gravity effect of geology is a small number. It's, depending on your target, anything from 0.1 to 50 milligauss. Well, that's pretty small compared to the 980,000 milligauss that we started out with. So the gravity from geology is a very small signal in the grand scheme of things, and there are many corrections that are necessary. Now, what are the challenges if we put a gravimeter in an aircraft? Well, all of a sudden you're in a moving platform that moves up and down, back and forth. And so as we move along, we're going to see that we're going to have several accelerations that impact on our test mass. We have acceleration due to the aircraft moving in space, so that's the kinematic accelerations. And they can be both upwards and downwards, depending on the movement of the aircraft. And they are summed with the acceleration due to the masses that are located in the ground below us. And so we run into the problem in physics called the equivalence principle, and that is that a gravimeter cannot distinguish between accelerations due to masses and accelerations due to kinematics, that's due to the aircraft motion. They have the same effects on the test mass. So what can we do? Well, one way is to accurately map the movement of the aircraft with, say, GPS, and then try to estimate the acceleration of the aircraft motion and subtract this from observations in order to isolate what we're interested in, is the acceleration due to the masses in the Earth below us. So we need to know the aircraft motion to very high precision to do that. And the question is, how high a precision do we need to know? And there are two big effects once you start doing gravity observations in a moving vehicle. And the first one is the Eötvös effect, and that's the effect discovered and characterized by Baron Lorenz von Eötvös. I mean, a baron that was a geophysicist. How cool is that? And Eötvös was able to show that if we're moving with the Earth rotation, then the centripetal acceleration that we experience will be, let's see, if we move with it, then we have more of a centripetal acceleration, and that means that the observed gravity will be reduced. Likewise, if we're moving the other direction, then the observed gravity will be increased because we're not rotating as much. And so the problem there is that that's a significant effect. With typical parameters, you end up with something like 500 milligauss. And remember that our signal was somewhere between 0.1 to 50 milligauss. So it's a big effect that we need to do something about. And it turns out that the calculation of the Eötvös effects described in this equation here contains latitude and heading and velocity. And turns out that this equation is very sensitive to any errors that you have in heading and any errors that you have in velocity. So we need to know our speed and our heading very, very accurately. With the current capability that we have with differential GPS, and we have a 50 centimeter precision accuracy, we can get down to about 5 milligauss error in our Eötvös correction. But someday in the very distant future, when we get down to 1 centimeter precision accuracy, we'll have something like 0.1 milligauss error, which is of the order of the smallest signals that we're currently looking for. Another problem is the vertical heave. The aircraft doesn't fly at a constant level. It bounces up and down ever so slightly. And it doesn't take much bouncing to introduce some very, very large gravity effects. If you have a 10 centimeter displacement over a period of 2 seconds, which, by the way, a 10 centimeter displacement we can't observe with present day GPS accuracy, or at least not record correctly. That means that we are getting in the vicinity of 50,000 milligauss. So we have a big problem with vertical heave. Luckily, the vertical heave is periodic. As the plane goes down a little bit, the pilot corrects and it comes up a little bit. So if we average over a sufficiently long time, then we can then the vertical heave will average out of the data. And a sufficiently long time turns out to be 100 seconds today. And 100 seconds give us about 0.7 milligauss accuracy on airborne gravity. Unfortunately, the plane will have flown 6 kilometers in 100 seconds. So as we average over observations over 6 kilometers, we're only going to end up with 3 kilometer resolution data. And that's the problem with using airborne gravity, is that the vertical heave and the averaging that we do in order to compensate for vertical heave really screws up our lateral spatial resolution. So right now, airborne gravity measurements are limited by precision accuracy, and we can do something about that if we, say, flew repeat lines, or if we flew slower. But really, significant improvements are only going to come the day that we get less than 1 centimeter precision accuracy with our aircrafts. So to counter this problem, enter the airborne gravity gradiometer. And here the idea is basically that we don't put one gravimeter, but we put 2 gravimeters in an instrument, and we bolt them together. And as we bolt them together at a fixed distance, and as they move, the 2 instruments, as we move through the air, the 2 instruments will experience the same aircraft motion accelerations. So now if we subtract those 2 observations from each other, then the aircraft motion will cancel out. And the only thing that remains is the difference in gravitational attraction due to the fact that the 2 instruments are at different distances to the say, this mass excess that's there on the ground below us. So we're looking at the gradient of the gravity, And by measuring the gradient of the gravity, and which is just the difference in the two observations divided by the distance between them, then we come up with an observation that to a large extent has had the aircraft's motion accelerations removed. The unit for a gravity gradient is Eötvös, after the cool baron that we saw a little earlier. And they end up being 10 to the minus 9th per second square. You can also think that as 0.1 milligauss per 1,000 meters. So the gradiometer data, as I said, avoids the equivalent principles, and it also turns out that there are much fewer corrections. All the corrections that we talked about before are not necessary as we do this subtraction of gravity observations, and we're left really just with the terrain correction that we have to do. So gravity gradiometers measure the difference in any component of gravity. I only showed you the difference in the horizontal difference in the vertical component, but you can imagine that you can have any combination of accelerometers that have sensitivities in different directions and measure the difference along different directions. So what we end up with is that, so remember, airborne gravimeters have typically 1 milligauss noise at 6 kilometers minimum wavelength. And the top of the line airborne gravity gradiometer instruments nowadays have an accuracy of about 0.1 milligauss at 300 meters minimum wavelength. So now we have an instrument that's can be used for mineral exploration. If we just briefly touch on what's the technology here, there are two, I suppose, major designs that have been released or that are in operation today for airborne gravity gradiometry, and they're both made by the technology company Lockheed Martin in the US. Here's the first design. It's called the FALCON design, and it's basically a group of four twinned or two pairs of radial accelerometers that are sitting on a rotating disk, and through some ingenious adding and subtraction of the signals from these accelerometers, we end up with two gravity component, one offline tensor component, and one that's the difference of the diagonal, two of the diagonal tensor components. And we can, of course, take this approach and then go from one disk to three disks. So if you have three rotating disks that are sitting in an orthogonal configuration, then you can end up with three cross-line tensor components and three of the diagonal difference components. And that system is called the FTG system. It sits on smaller disks in order to have enough room for three rotating disks. So we have three rotating disks here, and they're mounted orthogonally in an umbrella configuration. The latest development from Lockheed Martin is the enhanced full gravity gradiometer, which is basically the FTG with larger baselines. So the disks have gotten larger, which of course means that the instrument itself has become quite bulky as well. So, and sometimes in the future, about 8 years ago, 7-8 years ago, Lockheed Martin announced that they were working on a new development called the FTG Plus, but that's still in development. So that was the technology, or the sole technology provider of airborne gravity gradiometry instruments. Now the service providers are divided into, I suppose, two camps. You got Xcalibur Multi-Physics that fly the FALCON systems, and they have 6 systems in operation, flying in anything from large Basler aircraft. These Basler aircraft are converted DC-3 to smaller Grand Caravans, as well as a configuration that flies in helicopters. The FTG systems are operated or flown or offered to the industry by Bell Geospace in Basler aircraft, or by the newly rebranded Metatech. That also has 3 systems and fly primarily in converted DC-3 Baslers as well. Now let's have a look at the noise levels and the spatial resolution and the subsequent detectability in airborne gravity gradiometry. As we've seen, gravity gradiometry has been flown not only in helicopters and fixed-wing aircraft, but even in a Zeppelin airship for a short period back in the day. Why do we have these different platforms? Well, the key drivers are, of course, safety, and then the drivers could be that we're looking for slower speed in order to improve spatial resolution. We're looking for stable platforms in order to get lower turbulence and thus lower noise. We're looking to fly at lower altitudes in order to get improved spatial resolution from near surface targets, as well as improved signal amplitude. And finally, of course, we're looking for longer endurance so that we can have improved productivity and have associated low cost with the data. In terms of the published noise figures, this is from a paper that I published with Mark Dransfield about 10 years ago, and there's been pretty good transparency from the providers of the FALCON systems, but that transparency has been lacking somewhat from the providers of the FGD system. So we don't have much published information about the noise specs for the FGD systems. This was from a paper 10 years ago, and it hasn't really changed till today. I just heard rumors that one of the aircraft, one of the survey providers, has been flying a test survey on a test gravity test bed out in Western Australia, the Cowering test site. So I hope that soon we'll start to see some noise data coming out of that exercise. But to take away is that for the average FALCON systems, either in the helicopter or in the older non-digital model, the RMS noise on the vertical gravity gradient are of the order of 6 Eötvös. For the top of the line digital system, we're looking at probably about 3 Eötvös in the RMS noise. Of course, as we fly a long line, there's some low pass filtering that goes on in the data processing, and so that means that for both the FGG and the FALCON system, in a fixed wing we solve anomalies that are less than 150 meters apart. Once you're in a helicopter, then that resolution limit drops to 45 meters. Of course, your line spacing also influences the resolution that you have. If you're flying with line spacing more than 300 meters, then you'll start to degrade the resolution of both the FALCON and the FGG data. And so, for example, a survey that's flown either by FALCON or FGG at 1,000 meters apart can really only resolve anomalies of geological features that are more than 300 meters apart. 500 meters apart. So half of the line spacing that you're using. And then there's the noise limits. Well, we saw that the top of the line of the FALCON systems has a noise of the vertical gravity gradient around the 3 Eötvös mark, and about 0.1 milligauss. And the noise has zero mean, and it's Gaussian. When it's Gaussian, means that 95% of the noise will lie within plus or minus 2 standard deviations. So for a typical noise survey with a noise of 3 Eötvös, then 95% of that noise will be between plus and minus 6 Eötvös. That's the double of the noise estimate. And so a rule of thumb is that, if you're ever looking for a target, you want to detect it with gravity gradiometry, at least in the present day, it has to have a response that's larger than 6 Eötvös. It has to be able to peak out out of the noise. Otherwise, forget about it. And that, in gravity terms, corresponds to 0.2 milligal. So that's sort of the limit of detectability that we have with the published noise figures from what is currently the top of the line. How can we know whether a target is above, or a target that you're searching for is above 6 Eötvös? Well, if you have an analog, if you have a target somewhere and you've done some ground gravity over that, then you can just convert that ground gravity to the equivalent airborne gravity gradiometry data by just doing a first vertical derivative, upward continue it, and then multiply by 10,000 just to convert from milligal per meters to Eötvös. And that will provide you with a grid where you can examine the ranges in amplitude and see whether your target is observable by airborne gravity gradiometry. Otherwise, you're stuck with modeling studies. So you start making plantations of your targets and compute the responses from that. You might vary some parameters, anything from size to the depth of burial, and then you add a reasonable noise to that, and then you can start to examine whether a target is detectable or not. A couple of examples or a couple of advice there is that when you do this modeling, be sure to model the responses up at the flying heights. It's not at the ground level. And also be sure to add noise, and at 300 meter low pass zero mean Gaussian noise, that's been scaled to an RMS value of 6 Eötvös. That's a pretty good approximation. So that's my recipe for good airborne gravity gradiometry noise. And of course, you have to also be sure to low pass filter the model response before you add it to the noise. Typically use a 300 meter cutoff wavelength. That's what's being used in the data processing. So let's have a look at how we design an AGG survey. And to design a survey, surveys are flown basically as parallel traverse lines. They're typically flown in a racetrack pattern in order to avoid steep banking angles, and which introduces large horizontal accelerations. So the survey provider tries to avoid that. They'll also design the survey so that they spend maximum time online. So if you have a long, skinny survey, they will insist on flying along that long, skinny line, not traverse back and forth, so that they would have to spend most of the survey time turning. In terms of the parameters for survey design, the minimum length that most survey providers will accept is 10 kilometers. You don't do surveys that line lengths that are shorter than that. You need a 600 meter line in, line out for the fixed wing survey. That goes down to 350 meters with the helicopter, because that only flies at 60 knots, whereas the fixed wing typically flies at about 115 knots. Survey heights, safety dependent, but anything above 60 meters for the fixed wing and may say 35 meters for the helicopter. Line separation, well, that depends on the target. We'll talk about that a little bit later. In terms of tie lines, you don't need tie lines for the gravity gradiometry, but if you're having magnetics, it's a nice thing to have. And so tie lines are typically recommended at 10 times the main traverse spacing. The technology that's in any of the Lockheed Martin gravity gradiometry instruments is military technology, originally designed by the U.S. government for covert navigation in submarines. And so that technology is still under international traffic of arms regulation. So you can only fly gravity gradiometry technology, that gravity gradiometry technology, in countries that are approved under ITAR. What's the line separation you should have? And look, I've seen good survey data from anywhere from 5 meters up to 50 meters up to 6 kilometer line spacing. So of course, it comes, as we saw before, it comes with a larger wide line spacing, comes with a reduction in resolution. So line separation should be chosen to suit the target. And here, the important parameter is the height. It's the distance between the aircraft and the depth of the target that you're interested in. And if you're just looking at detecting something at that depth, then you should have a line spacing that can be twice that height. If you want to map it, then you should have line spacing that's equal to that height or less. And if you want to model something, then you should have a line spacing that's equal to half that height or less. And so those are really good rules of thumb. What's the effect of changing the line separation? Well, here's an example from Rutherford Dome, and here we've used on the left here 1 kilometer line spacing line, and then we flicked out every second line and reprocessed the data all the way from scratch, and this is what it looks like. And then we've taken this data here and taken only every fourth line, so we get 4 kilometer line spacing, and then reprocessed that from the very beginning. And so here are the results. So as you can see, you end up with diminished resolution, both a long line but also cross line, as you would expect. In terms of the height guidelines, well, I recommend that you fly terrain draped surveys. The system is robust enough to deal with that. That means that you get maximum signal by flying as low, whilst it's still safe. If your target is very deep, if your target is down at a kilometer, it makes really no difference whether you're flying 60 meters above the ground or 120 meters above the ground, because that has very little percentage difference in the distance to your target. And so, for God's sake, let the pilots fly at 120 meters just to give them some safer buffer and envelope. Also, if you insist on flying lower, you need to know the aircraft position much more accurately, and you need to know the topography with much more detail in order to do terrain corrections. In terms of line direction, it turns out that the gravity gradiometry is remarkably insensitive to the strike of the geology. So line orientation really doesn't matter that much in my experience. So in summary, when you go out and design your gravity gradiometry survey, the minimum line length is 10 kilometers for the fixed wing, 6 kilometers for the helicopter. You got to choose line separation that suits the target. We talked about that. You can fly a draped survey at a height that's safe, and line orientation is luckily fairly insensitive to geological strike. Now let's leave all the technology behind, instead just have a look at some case studies. So let's have a look at geological mapping, regional mapping first. And this is an early example flown by BHP in Northwestern Territories in Canada. And here we have the geology map over the Ekati region. This was flown for diamond exploration, and it's about a 70 by 50 kilometer survey. So it's a pretty large survey, and we can see that there are different geological domains. This is the Canadian Shield, so lots of granites, lots of monzogranite and granodiorite, and then we've thrown in a bit of greywacke and some mafic intrusions as well, just for fun. And so if we look at the geology map and then look at the AGG, the vertical gravity gradient in grayscale, we can see that there is actually a fair bit of domaining going on in the data set, and we can start to see some of the features that are associated with the mapped ground geology. We also see some dikes running through there. They're the thin white lines, and all the black gravity lows are either depressions in lakes or they are diamondiferous kimbolites. If we look at the gravity that's been derived from the gravity gradient, and that's one of the deliverables that you'll get from any survey provider, then we can see that the corresponding gravity focuses in on the longer wavelengths, whereas the gradients has much more focus on the shorter wavelengths. And so by using the two, we can start to do some serious geological mapping and domaining in this area. Here's another example, also from Canada. That's from New Brunswick. This example is an example from the FGD system. Again, we have a survey that's all about 70 by 50 kilometers. And here we have the geology, and here we have the magnetic field reduced to the pole. And then if we compare the magnetic field to the gravity gradiometry that's coming out of the FGT system, we see that there's a lot of complementary information that's not necessarily in the TMI, but that stands out in the gravity data. And we see that some of the more sharper lithological boundaries that have been mapped, you see very clearly in the TZ set in the vertical gravity gradient, but the derived gravity are not quite as clear, and that's because, as we were talking about, the gravity tends to focus on the longer wavelengths, and by that you focus on typically on deeper geology, not the geology that's at the very surface. Now let's have a look at two specific target styles that's been pursued very successfully with Airborne gravity gradiometry, and we'll start to look at iron ore. And iron ore here in this case, we're looking for hematite-rich deposit instead of your ordinary magnetite-rich banded iron formations. And there it is so that if you have a magnetite-rich iron ore, that's dense, so it have a high signature, but the magnetic signature will also be well-defined as a well-defined high. However, if you have a hematite-rich ore, then the magnetites, the amount of magnetite has been reduced, and so you have much lower magnetic susceptibility. So whilst the hematite will still have a gravity signature high, there'll be absence of a significant response with regards to the magnetics. And so to distinguish magnetite from hematite, you can need both magnetite and gravity signatures together. And here's an example from the Pilbara, where we're looking at Martite, Microplaty Hematite. And here's an example where we have magnetics here on the left, and we have gravity gradient on the right. And we have, looking at the gravity gradient, we have a number of gravity highs, but we see that two of them outlined in one. The economic deposits, whereas this high here is also associated with a magnetic high, and we see then that is an uneconomic deposit. Another ore type in the Pilbara is the Martite-goethite ore, and that's reasonably important because it comprises about 90% of the resources of the bedded ore in the Hammersley region. And if we, as an example, look at a modeling that's been done for Martite-goethite ore, we see that small Martite-goethite ore in the Marramamba, as well as in the Brockman Formation, will result in small gravity highs, whereas you might get a false anomaly as well from the Wittenoom dolomite that also produces a gravity high. So you need to, when you do exploration in these areas, you need to have your stratigraphy at handy and understand where you are in the sequence. If we look at a magnetic survey flown over mining area C, owned by BHP, a significant deposit at 3.3 gigatons of ore at 60%, then we see that there's an absence of magnetic responses from a number of the deposits that are sitting along this unit here. The A deposits, C deposits, D deposits, and E deposits. Even if we look at the first vertical derivative, there's not much of a magnetic response. However, if we look at the vertical gravity gradient, all flown over the same area, we see that all of these deposits are associated with a localized gravity high. And so the combination of a gravity high and the absence of a magnetic expression is a good vector for exploration in the Pilbara. Another area where airborne gravity gradiometry has shown to be popular is in iron oxide copper gold exploration. And so I'm just going to show some examples of airborne gravity gradiometry over known IOCGs, Ernest Henry and Prominent Hill, and then we'll just look at two deposits, two explorations, discoveries, both in Zambia and in Chile. If we look at Ernest Henry, when it was discovered, it had been completely undercover. This is a blind discovery, and so there's no indication of the geology at the surface. It was regional mag that allowed the mapping of the geology undercover and prospect selection. But we see that here a gravity gradiometry survey combined with a magnetic survey had been flown, and here's the location of Ernest Henry. And we see that the deposit is associated with near coincident gravity and magnetic highs. And that's typical for IOCG deposits. Another example is the Prominent Hill in South Australia. And here on the left, we have the ground gravity data that was acquired before the discovery. And so the data is from 400 to 800 meter station intervals. There's some patches of 100 by 100 meter station spacing. And after the discovery, an airborne gravity gradiometry was flown, and here's the derived gravity from that survey. And we see that there's an excellent correspondence with the ground gravity. And we see that, the FALCON survey, in this case here was a FALCON survey, it was post-discovery, but it clearly would have discovered the Prominent Hill. And what you see at Prominent Hill as a target vector there was the barren hematite. That's the core of the deposit, with the copper and gold sitting as an onion skin around the edges of it. Now, having seen that, let's go and have a look at a discovery that was made in Mumbwa region in Zambia, and the project here is in the southern margin here of the Lufelian Arc tectonic province, and there's been a large granitic complex that's been intruded nearby. The physical signatures for IOCG deposits is that we're looking for areas that are close to large-scale granitic magnetism. We're looking for areas at high to extreme amplitude magnetic and gravity anomalies. And we're looking for areas with close to regional domain-bounding faults. The deposits themselves have structural control, so we're looking for intersections of lineaments, dilational jogs, or fault beds. And there's many areas that have an anomalous high uranium contents in the host rock sequences as well. So a survey was flown over this Kitumba Mutoya prospect here. There was some artisanal mining that occurred. And so here is the LiDAR terrains, and we see that the hook granite batholids are sitting up here. If we look at the TMI data, the magnetic data, we see that there are several intrusions of the hook granite province complex here, as well as a regional fault coming through here, the Kankuma fault, that's been intersected with the Mumbwa fault zone. There were some strong magnetic anomalies in this region, from 3,000 nanoteslas up to 10,000 nanoteslas. So that's worth noting. If we look at the first vertical derivative, we see much more clearly the multiple intrusive events up here in the hook granite province. If we look at the gravity, we see that there's a fundamental change in the lithological domains along the Kankuma faults, and that's because the Kankama fault is a major lithological boundary, and it's regional. We also see there's very strong gravity anomalies between 5 and 14 milligauss in this region here. This, by the way, is the location of the discovery hole. And we see that the granite hook complex comes up as gravity lows, whereas there is a number of gravity highs sitting down here on the other side of the Kankama fault, and these are probably more mafic intrusions. And the ones that have gotten closest to the surface are mapped in very good detail when we look at the vertical gradient here. Now, when we look at the vertical gradient here, we can see that the ones that are near surface are mapped well. If we look at the uranium for the area, we see that there's a distinct uranium anomalism around here at Kitumba, about 60 ppm, and Mutoya over here is about 20 ppm. This is on a very low background of maybe 4 to 5 ppm. So this survey sort of really upgraded this project, and a drilling program was started. And it was started because we really checked all the boxes. We have nearby continental granitic magnetism. We have high to extreme amplitude magnetic and gravity anomalies. We are within, well, we're right on a major regional domain bounding faults. We have an intersection of lineaments as well as a dilational jog. And there's anomalously high uranium contents in the host rock sequence. And so the owner of the tenements could announce a discovery from the discovery hole S36001, and that was cited on FALCON survey data. And so that included about 600 meters of 0.5% copper. And that was later followed up a couple of years later by a drill hole nearby that contains, well, 200 meters of 5% copper. And so I just wanted to show that the area is leached, so not very much copper in the first 200 meters, but then we get all the leached copper coming in, and we have kicks up to around 25% copper in the top area. Another example I just quickly want to show is from the Chilean IOCG belt, and this is Santo Domingo Sur, and a FALCON survey was flown there. And whereas magnetics and IP had not been able to delineate mineralization, then we see here that the Santo Domingo Sur mantle style IOCG is coincident with this gravity high, and that the mineralization continues up towards the north and over towards the west along these gravity highs. And over here we see the satellite deposit of Iris Norte, and Estrelita. And Far West Mining, that was the discoverer of this here, as an indicated resource of I think almost 400 million tons of 0.6% copper. So as an end, just want to show you that the FALCON clearly outlined the in black here we have the outline of the deposit, and it's coincident with the gravity high, whereas the magnetics is not able to clearly pinpoint the mineralization to the same extent. And to end this, I'd say that, look, the US government probably spent about hundreds of millions of dollars for the development of gravity gradiometry technology for military purposes. And once that information was declassified, then BH Billiton took that information, again spent tens of millions of dollars of making this submarine technology suitable to be flown in an aircraft. And yet, you know, we only need one deposit of this size to have created value of the orders of billions of dollars. And so I see this as an incredibly good investment by the players in this area, and I see gravity gradiometry as something that will continue to be used, and to be used successfully in minerals exploration. So with that, I'm done with my rather longish presentation, and thanks very much for coming today. But if you have any questions, I'll be happy to answer them in the time that we have left. Thank you.
Thank you so much. That was wonderful. It's been amazing having you on, so thank you.